My name is Carl Steinbach. I'm an engineer at Citus Data. I'm also, a member of the PMC and a committer on the Apache Hive project, which is kind of like a database project related to Hadoop. In the past, I've worked at a bunch of enterprise software companies, most recently Cloudera, where I was team lead for the Hive team. I've also spent time at Informatica, NetApp, where I worked on storage security products, and Oracle, where I sort of started my professional career working on the database server. My other sort of claim to fame is that I wrote that blog post about Tom Lane's email habits, which I think a lot of you have probably read. Thank you very much. Hopefully this presentation lives up to that blog post. Anyway, I've given talks on this topic a couple times in the past, and from those experiences I've learned that it's a good idea to sort of start up front by making sure that we're all on the same page about what a distributed analytic database is. I think probably 95% of people, when you say relational database, they automatically think OLTP, the standard sort of create, update, delete use case scenario with transactions. And an analytic database is definitely not OLTP. It's typically referred to as an OLAP database. So the kind of things that you're going to do with an OLAP database include processing, let's say, clickstream events, or processing log files, or processing some kind of event or fact type data. And typically, people are going to do aggregations on those data or big joins. But in terms of the way that the actual sort of like database behaves, one thing that sort of defines OLAP use cases is large sequential scans, where typically you're looking at the entire table as part of a query. Another thing is they're not really transaction oriented. So a lot of the stuff that you see in OLTP databases don't really apply. And then I think finally, and this is probably most important to the rest of this presentation, in terms of the performance characteristics of OLAP databases, they are typically I/O bound. So if you're looking for sort of the performance bottleneck in the system, it's not going to be the CPU. It's typically going to be the rate at which the database process can actually pull information off of disk. So a lot of work over the past 10 or 20 years has gone into like figuring out how to reduce the impact of that bottleneck or eliminate it altogether. So one thing that also relates to what we're going to discuss is the enterprise storage model. And this is something that's evolved over, let's say, the past 20 or 30 years. And the goal of this is to basically solve the problem of availability and accessibility for data in the context of, let's say, a large enterprise, a company with 10, 100, 1,000 employees and terabytes and possibly even petabytes of data. So obviously, that data is not going to sit on one computer. It's going to sit on a bunch of computers, and you want somehow to make it accessible to a large number of people in your organization. So you need to be able to access it over a network of some sort. And the sort of solution that's evolved to this over time, and really that a whole industry has been built around, is basically structuring your data centers such that you have a pool of storage. And this could be in the form of a NAS or a SAN. And then it's connected via some kind of switching network fabric to a pool of compute resources. So there are a couple problems with this. One problem that customers feel immediately is cost. This is a really expensive solution. This is a lot more expensive than going out and buying a hard drive at Fry's Electronics or Best Buy or something like that. I mean, you're talking about spending $1,000 or upwards of $1,000 per terabyte, probably even more conventionally. And then add to that the fact that these systems have sort of a built-in scalability problem. And the scalability problem is that really big pipe that sits between your island of compute resources and your island of storage resources. So as you attempt to scale out your storage pool, you're going to have to make that pipe bigger and bigger and bigger. In practice, I mean, there are sort of limits to how big you can make that pipe. There are also limits to how consequently, how much you can scale sort of the underlying storage tier. And what happens as a consequence is that people tend to sort of partition these resources, which means they'll end up with multiple islands of storage pools and multiple islands of compute workers, and then that adds on top of it an additional manageability problem. And there's sort of a whole industry that's grown around just solving that, helping you to shuttle data from one storage pool to another to meet SLAs or jobs that you have running in the background. I also want to say that this diagram is sort of a gross, oversimplification. I'm trying to get the main points home, but I wanted to point out that, besides just having like a storage pool, there are actually, in a sense, multiple different tiers of storage pool with different sort of price performance characteristics. So oftentimes in the compute pool, you might have an OLAP database, and that database will have its own sort of private storage pool, which will often be, in terms of cost per terabyte, much more expensive than sort of your larger pool of online storage. And consequently, you fall into this usage pattern where you're always sort of moving data between these two pools, because you can't fit all of the stuff that you want to look at in the sort of fast, small pool of storage. And as a result, like, there are pretty big management headaches. So over 10 years ago at this point, the folks at Google were building this gigantic search engine, and in order to build the inverted index that they needed to power that search engine, they were collecting these gigantic data sets by doing web crawls. And I think they realized pretty early on that if they got hooked on sort of the NAS or SAN solution, that would not be just a bottleneck for their data center, but it would really be a bottleneck for their business. So they knew that they had to find a different solution to that problem, and they knew that whatever solution they ended up with, it had to both be inexpensive and it had to be very scalable. So the sort of design priorities that they set out were, first off, we're going to base this on commodity hardware. We want the hardware that the system is built on top of to be as inexpensive as possible. And sort of a consequence of that is when you go with inexpensive commodity hardware, you expect the stuff to fail all the time. And if you're deploying 1,000 of these boxes, you expect probably one box to fail every day, if not multiple boxes. So you have to have a system that can be resilient in the face of these constant failures and outages. So another really, I think, interesting thing about this is that the solution that they came up with, of course, is referred to as the Google file system. But in many ways, it's not really a conventional file system. It's more of, let's say, a distributed block store. And there's some sort of interesting, there's an interview online that you can find with Sean Quinlan, who was one of the original architects of this system. And he sort of talks about the genesis of how they came up with this sort of set of priorities and the things that they decided were not so important. And I think one of the really critical things is that they weren't worried about supporting or building a POSIX file system. They weren't worried about supporting random reads or random writes. So there was a lot of stuff, a lot of sort of like file system dogma that they just dispensed with very quickly. And in the interview with Quinlan, he makes the point that since the people who were building GFS were actually the same people who were building the system on top of GFS that were consuming it, that they were able to sort of be very fluid in terms of defining what the requirements were for this system. And I think that's kind of, it's an interesting thing to think about in terms of how we build systems in the future, right? That sometimes just these sort of like little political disagreements between groups at different layers in the system can really stymie advances like this. So the system that they ended up with was referred to as the Google file system, and this is sort of a high-level overview of how it works. So when a file is written to GFS, it's basically split up into a number of fixed-size chunks. So in the original GFS implementation, these chunks were 64 megabytes in size, which is a lot larger than the blocks that you find in a traditional file system, but it makes sense in the context of storing files that, on average are going to be gigabytes, if not potentially even terabytes in size. And the advantage, of course, of having big blocks, or at least one really significant advantage, is that it reduces the metadata load on whatever system you're using to store the file system metadata. There's less of it to store since the number of objects that it needs to track and keep track of are limited in number. So another sort of significant design element here is that once that file is split up into chunks, those chunks are then parceled out more or less randomly to a set of chunk servers. And 3 copies, or whatever the replication factor for the file system are, by default 3 copies would then be distributed across the chunk servers in the system. So there are, in one sense, this is very different from the way that sort of traditional distributed file systems achieve reliability by using something like RAID or a parity-based striping mechanism, which is more efficient in terms of the amount of disk space that's used. I mean, you're able to, let's say, if you use, RAID 5, you're basically, trading off like 1/5 of your storage space for that additional reliability. So this is a lot less efficient in terms of disk space, but because they're actually creating multiple copies of every chunk, they do get some other benefits in return. So one of them is that the load can be distributed very evenly across these chunk servers when the same file is being read by multiple clients. So basically, a coordinator has the option of saying, if these 3 clients are reading the same file, they don't necessarily have to all talk to the same chunk server. Another advantage of this is that in the system that they devised, they expected not just to have disk failures, but they also expected to have chunk server failures. They expected the whole node to just disappear and go down. And at that point, if you're basically building chunk servers on top of RAID, the RAID wouldn't matter, right? Because you lose the chunk server as an entire unit. So this way, when a chunk server goes down, you have 2 other chunk servers available where you can read the same block from. And finally, the other nice sort of characteristic of this is that when a chunk server goes down, since the basically like all of the blocks that are on that one chunk server have replicas distributed in a more or less uniform fashion over the remaining chunk servers, the load that's required in order, to sort of read those chunks back and copy them to a new chunk server in order to maintain the replication factor is then distributed evenly across the other servers in the pool. So earlier I mentioned that the problem that Google was sort of contending with was twofold. They were worried about the cost of the sort of traditional NAS and SAN solution, and they were also worried about scalability. So I think, if you look at just the stuff that's described in the original GFS paper and you hold it against these goals, based on what they articulated in that paper, it's pretty clear that they solved the cost problem. I mean, they articulated a way of building a very scalable file system using commodity components. But I don't think that if you look at just the GFS paper that they really solved the scalability problem. Because fundamentally, it's still a client-server type of file system where the clients are all going to pull data across the network, and that network is then going to become the I/O bottleneck. And it wasn't until a year later, when they published the MapReduce paper, that the missing puzzle piece appeared. And it was in the MapReduce paper where they said, no, actually, here's how GFS works. This is not a conventional file system where you have clients that are pulling data over to the client in order to do work on the data there. Instead, we are going to take the work and push it over to the data. So MapReduce is basically a distributed computing framework that allows you to send work over to the nodes where the data actually exists. And by sort of maintaining data locality, you almost completely eliminate this network bottleneck problem. MapReduce does require some network traffic between nodes. It has a shuffle and sort phase and stuff like that. But at least at a first order, you've basically eliminated this really significant bottleneck. And that I think is the key benefit of Hadoop and of HDFS. And it's, I think, really interesting that if you just look at the GFS paper, that this missing piece is not mentioned anywhere there. But if you go back and you read that paper, you can tell that that's what they're thinking. It's kind of sort of an interesting historical thing. So, these papers were published in 2003 and 2004. And at around that same time, Doug Cutting and Mike Caffarello were working on an open source project called Nutch, which was an outgrowth of Apache Lucene, and their goal was to build an open source search engine. So they saw these papers and they realized immediately, hey, this is clearly the way that we have to build Nutch. We need to build a distributed file system equivalent to GFS, and we need to devise our own MapReduce implementation. And that's what became Hadoop. So Hadoop is these two things: HDFS, which is Hadoop's version of GFS, and then their own MapReduce implementation. So that project came into existence in 2005. It was initially used quite heavily at Yahoo and then Facebook. And in the last, I would say, 3 to 4 years, we've seen sort of more general adoption within enterprise data centers. So my previous employer, Cloudera, has sort of built a business around helping companies that are let's say already using Oracle or already using SQL Server or something like that to figure out ways of sort of transitioning to this lower cost and more scalable infrastructure. But the fact that people are actually using this in industry has given us an opportunity to get a sense for what are the practical benefits of Hadoop and also what are the drawbacks. So in terms of benefits, I think at the very top of the list is the way that HDFS has commoditized enterprise storage. And this has had really significant effects in terms of what enterprise organizations are doing with their data, and also the amount of data that they're actually retaining on site. So in the past, and actually still today, you find that most large organizations have some data that they maintain in an online fashion in their data center, but a lot of the data that they collect is getting written to tape and put on a truck, and the truck drives to a cave somewhere, and it's deposited there, and no one ever looks at it again. And some of you guys might think I'm joking about the cave thing, but you should look up Iron Mountain, which is one of these companies. They literally have a cave. So that's one major thing. Like companies that were formerly putting a lot of data on tape, never to be seen again, are now maintaining it in HDFS instead, and they're able to derive a lot of benefit from that data. Another big advantage is the way that HDFS allows companies to scale out in a genuinely fashion instead of having to invest in more expensive hardware to scale up. It also gives them the ability to run a system in a fault-tolerant manner, I think in a manner that wasn't really available before with other sort of existing NAS and SAN solutions. And it's also introduced a new level of flexibility in terms of the data that these organizations can operate on. So one of the things about Hadoop is that it is, or HDFS in particular, it's sort of a write once, read many times file system. It's sort of like an online archive file system. So the ability to operate on data in place in the format in which it lands on disk is very attractive. And Hadoop offers flexible tools that allow you basically to extract information from a variety of different formats. So, So at the same time, I think people are aware that Hadoop has a bunch of drawbacks, and chief among these is MapReduce itself. MapReduce is very powerful in the sense that it's extremely flexible, but a lot of that flexibility comes from the fact that it's so generic or so general and also so low level. So to do even sort of simple operations, you're going to end up writing pages of Java code. And once you've written this code, it's more or less impossible to maintain. I mean, you're going to have trouble remembering a month later what the code you wrote does, and your ability to share it with a coworker is close to zero. So part of this relates to the fact that MapReduce doesn't have any schemas, and schemas are really valuable. I think many times when people think about schemas in the context of like a relational database, they maybe think that in some ways schemas are the enemy, right? Because oftentimes you'll find that before, maybe you have some data that you really want to analyze in the database, but before you can even get it into the database, you have to talk to your DBA, and your DBA is going to spend a couple of days trying to figure out the right schema for this data. So there's a lot of latency, a lot of sort of organizational latency built into this. And the reason for that is that if you get the schema wrong, that's an expensive mistake to make. So schemas in sort of the traditional context are a high stakes game, but they also provide a lot of value because they allow you to view data in a logical fashion as opposed to having to worry about the underlying physical structure of it. And Hadoop, without schemas, forces you to constantly worry about the underlying physical structure. And then the other missing features, I think, can quickly be summarized by saying that people really want Hadoop to look more like a database. They want Hadoop, they like the scalability, they like the flexibility, but at the same time, databases look the way they do for a reason. They've evolved over the past 20 or 30 years in response to the needs of users, and they provide a bunch of features that make a lot of sense when what you're trying to do is analyze data. So these include things that help you write code or help you write better code, like optimizers and indexes and views. And there's also this large ecosystem of tools that run on top of databases that know how to speak things like ODBC and JDBC, and which allow you to do really interesting things with your data, like business intelligence tools, ETL tools for transforming and manipulating your data, and then things like SQL IDEs or other environments for doing data analysis. So the way that the Hadoop community responded to these shortcomings of the sort of core platform was by building a variety of domain-specific languages on top of Hadoop. So the idea was you no longer have to code your job in MapReduce. Instead, you can use this other language, which we compile down to MapReduce. So there were a variety of languages that evolved like this. Google, of course, has something called Sawzall, which they published a paper on. They also have a SQL DSL referred to as tensing. Within the Hadoop world, we have things like Pig. We also have cascading, which is kind of like a Java data flow API. The layer, though, or the DSL that I think has gained the most interest and adoption within sort of the enterprise software community is Hive. So Hive, made the very pragmatic decision. Instead of inventing our own language, we're going to stick with SQL. Because SQL has some rough edges, it has some bugs, but at least we've learned what those bugs are over the last 30 years, and they're easy to work around. And also, it turns out the entire world basically speaks SQL, including all of those ecosystem tools that I mentioned earlier. So it's sort of like as soon as, SQL is like the Esperanto of data processing, except that people actually speak it, unlike Esperanto. So anyway, that's the situation we're in. So one thing about Hive that I really want to sort of like try to convey is that most people, when you mention it, they think, okay, Hive is like a sequel to MapReduce compilation and execution engine, which is very true. That's what it is. But it's also these two other things that I don't think it gets enough credit for being. So one of those things basically is the data model that it provides. And by data model, I mean the way that it basically allows you to map logical structure in the form of schemas to underlying physical data that can be in basically any format you want. So in order to provide that functionality, Hive has two components. One is the Hive Metastore, which basically allows you, you can think of it as Hive's table catalog. So the Metastore maintains mappings of the form table basically to underlying file in HDFS, or to HDFS location where the data is stored. And it also maintains mappings of table to SERDI name, where SERDIs are basically these plugin libraries that allow you to handle different formats. So with these two bits of information, when Hive executes a query plan, which is in the form of basically a graph of MapReduce jobs, each one of these MapReduce jobs gets sent to a data node, which you could think of as HDFS's version of chunk servers in GFS. And the MapReduce job, which is expressed in terms of Hive operators, is executed there. But the data, as it's read off of HDFS, is filtered through one of these SERDIs. So an example would be, let's say, a CSV SERDI, or a JSON SERDI, or perhaps an RC file SERDI, which is Hive's columnar format. But in this way, it allows you to do something really cool, which I think people have started to refer to as schema on read as opposed to schema on write. So this is sort of the really, I think, the really cool benefit of Hive, and the thing that I expect will sort of be Hive's lasting impact on the database world. Not SQL to MapReduce, but this very like flexible way of mapping logical structure onto underlying physical data. Yep. So basically, a SERDI, by the way, SERDI stands for serialized, deserialized. So, sorry? SERDI, S-E-R-D-E, yeah. So when you are deserializing, you are basically reading from a file, and what you are pulling out of it are rows split into columns with types, okay? And in the reverse direction, you feed in basically these structures that are typed columns, and then it writes it out to the underlying file. So you were saying, could you have a SERDI that goes from CSV to, let's say, JSON or something like that? You'd actually use two SERDIs for that process. You would use a JSON SERDI and a CSV SERDI, and what you would do would be to construct two tables, one of which is based on top of JSON, the other on top of CSV. And then one interesting thing about Hive is that it's added a variety of sort of extensions to base SQL, including semantics that allow you to easily do things like stream data from one table into another table. So I hope that answers your question. So, I think Hive solved a bunch of problems, but in many ways it's also been sort of a victim of its own success, because as soon as you start making something look like a database, people are like, hey, this is great. I like that it looks like a database, but I wish you would cover that remaining 50% and make it look completely like a database. Where are this missing SQL feature that I'm used to using? Where is the authentication and authorization system? Here's a data type that I expected you to support as part of the SQL standard, but I don't see it here. And then another problem with Hive from the standpoint of many users is caused by the fact that it's basically delegating execution to MapReduce. So MapReduce is a very powerful tool, but it makes some compromises which are probably not the best compromises to make in the context of a database engine like Hive. And the big compromise that it makes is that it's batch-oriented. So it guarantees basically really high throughput, but it has this sort of built-in latency as a result of the fact that when you start a job, you have to talk to the job tracker, and the job tracker has to go and parcel out jobs to each one of the data nodes, so that as a result, even if you are running a query against just a small sliver of data, let's say a megabyte or 100 megabytes or something like that, the minimum sort of turnaround time on that query is going to be 15 to 30 seconds. And if you ran the same query, let's say on PostgreSQL on a single node, you'd expect it to complete in under a second. So with Hive, this sort of like whole sort of way of interacting with the database where you do sort of very small exploratory queries to try to gain like an understanding of the layout of your data and what's actually there, it's not really feasible or practical with Hive. So in the past year to maybe 2 years, I think it's fair to say a sort of new generation of distributed analytic databases has emerged, which are largely being designed to sort of solve this set of problems, and in particular the problem of the latency overhead and inefficiencies that are introduced by using MapReduce. So examples of these systems would include things like Impala from Cloudera, the Apache Drill project, Google's Dremel is an example of this, also within Google, and CitusDB is another example of that. So I'm going to talk a little bit about CitusDB, but before I do, I wanted to show sort of the common like architectural difference that sets these new databases apart from, let's say, the previous generation of MPP databases that emerged over the previous decade. So this looks a lot like what we've seen recently, where people have been adapting MPP databases to run on top of Hadoop. And what they're effectively doing is creating a connector between the worker nodes in the MPP cluster and the data nodes in HDFS. And the problem with this approach is that you have the I/O bottleneck between these two layers. So you're not achieving data locality for your jobs, and a system like this is just not going to scale. But the solution, is, at least if we want to illustrate it graphically, it's pretty straightforward. You get rid of the dedicated MPP data nodes, and you take the processes, the worker processes that were running on those nodes, and you co-locate them on each one of the data nodes. So in effect, what you're doing then is pushing the work down to the data, as opposed to pulling the data over to the work. And this allows systems like this to scale out in the same way that you're able to scale out with something like MapReduce. So I wanted to go into some more detail about how this actually plays out in a system like CitusDB. So CitusDB is built on top of PostgreSQL. And if we look at the components in the system, on the left-hand side we have PostgreSQL clients, ODBC and JDBC driver. And I think this is one of the really significant points I wanted to make, that as far as a client is concerned, as far as a user is concerned, CitusDB looks almost identical to PostgreSQL. So you can basically continue to use pSQL or the different tools that you're familiar with. The support for SQL is virtually the same. All of the same system tables are there and stuff like that. But in terms of changes we've made, on the master node, once again, it's more or less stock PostgreSQL with the addition of our distributed query compiler and execution engine. And then on each one of the HDFS data nodes, we co-locate what is in effect a stock copy of PostgreSQL, along with a foreign data wrapper that we've written that allows us to basically read from HDFS. So I wanted to go into a little bit more detail about how this actually works by giving an example of how a query is executed. So to start off, when you create a table on the CitusDB master, you would basically specify a directory or a file in HDFS that logical table name needs to map to. And then as part of a prior offline step, the master node syncs file system metadata off of the HDFS name node. So this basically allows it to map, it allows the master node to map an HDFS file name to a set of blocks and data nodes in the underlying storage pool. And then once the table is created and once the metadata has been synced, the master node talks to each one of the worker nodes, and it creates a foreign table per block on each one of the data nodes using the HDFS foreign data wrapper. So then subsequently, let's say the user submits a query, a simple aggregation query, to find the average salary of managers, in the organization. So as a first step, we take that global query and we rewrite it as a set of queries or fragment queries that can be executed on the worker nodes. And those queries then, or there's effectively one query per foreign table, where each foreign table maps to a block on each one of those data nodes. The worker nodes execute those fragment queries, generate partial result sets, which are then returned to the master node, which merges those results together and returns a final answer to the client. So there are some sort of interesting details that I wanted to cover at a slightly lower level. So one of them has to do with block awareness. So I had that previous slide where I showed that in a sense what we're doing is taking a traditional MPP database architecture, and the most significant change we're making is that we're co-locating the worker processes on the data nodes. But I don't want to leave you with the impression that that's all you have to do in order to achieve data locality. Because the problem is that if that alone is what you do, those MPP worker processes running on the data nodes are still going to have to basically fetch data from all of their neighbors in order to satisfy any query. So it's very important that the master node, when it is scheduling a query, when it is scheduling those fragment queries, that it sends them to the correct data nodes so that those data nodes can do those reads locally. And that's what we refer to as block awareness. So, another thing that's worth mentioning is fault tolerance. So our solution to fault tolerance, I think, can quickly be summarized by saying that we're basically leveraging the best features of the two platforms that we're building on top of, Hadoop and PostgreSQL. So what happens if the master node fails? Well, we take advantage of PostgreSQL streaming replication to make sure that the table metadata is copied over to a hot standby, and that solves the problem at the master node level. And at the worker nodes, since we are actually delegating the storage problem as well as the fault tolerance problem to HDFS, if one of those nodes fails, we already know that the actual data has been replicated to a bunch of neighbors and can quickly fail over to them. The sort of missing piece, the piece that we actually had to implement on our own, is the ability to, if a process or if a query is in the process of executing, detect that a node which is responsible for some of these fragment queries has gone down, and to reassign those queries dynamically to other replicas in the system. So, one of the things that I think, yep. Gets to the last of the replicas. Right. Then you're screwed, basically. Yeah. You would get an error back. That's true. And you would get an error back quickly because it would determine that it can't talk or it can't communicate with any of the three replicas in that situation. So I mean, there is a limit to Yeah, no, fair question. Fair question. So back when I was first talking to the guys at Citus Data, about joining the company, they were talking about what they had done with Citus DB and how they had built it on top of PostgreSQL. I wasn't very familiar with PostgreSQL at the time. My main, I was mainly familiar with things like MySQL, and in particular with things like Hive. And as they were telling me about some of the different features of PostgreSQL that they were leveraging, they mentioned foreign data wrappers. And I got really excited about this because foreign data wrappers, I quickly realized, are really a much more powerful version of Hive SerDes. Using foreign data wrappers, we are able to achieve the same sort of novel benefits that separate Hive from sort of traditional databases. The ability to do schema on read as opposed to schema on write, which introduces this whole new level of flexibility. And very significantly, schema on write is more, or schema on read is more than about just flexibility. It's also, in a sense, about performance. Because if you can read data in place, regardless of the format, without first having to go through this process of loading it, in other words, translating it or converting it into the native format of the database before you can read it, that's a significant performance win in terms of overall latency. And just as a quick side note, a couple of weeks ago, or maybe a month ago, someone posted a performance comparison between Hive and Amazon Redshift, and this was carried on Hacker News. And the sort of high-level thing was, Redshift does this query in 30 seconds, and it takes Hive 10 minutes or something like that. But what they left out was that it had taken 17 hours for them to load the data into Redshift before they could query it. So it's very important to consider both, I think, time to query as well as time of query when you're talking about these problems. So another significant thing about foreign data wrappers is that since it's a public API, it means that we can use this as an extension point and continue to build on it without having to worry about forking the code. I mean, without foreign data wrappers, we could have defined this API on our own, but it would have been a very brittle thing to have to maintain. And I think more often than not, what you see, definitely you've seen this happen in the past with other companies that have built distributed databases on top of Postgres. They end up basically forking pretty early on. One of our design goals from the very beginning has been to structure CitusDB in such a way that it's decoupled enough from PostgreSQL that with each new version of PostgreSQL, we can, let's say in a matter of weeks, rebase the changes that we've made onto the new version and then deliver to our customers both the value that we've added as well as the new features that the community has provided. And that's something that we're really excited about. Yes? That's probably a better question for my coworker Samid to answer. Okay. So let me just say that I love foreign data wrappers. I think that they are like the coolest thing ever. But if there's one thing I don't like about foreign data wrappers, it's the name. Because I think that it seriously undersells the power of this API. And in particular, when you're trying to talk to a customer or an analyst and you use the word foreign data wrapper, and you're like, yeah, this stuff is awesome. We're using foreign data wrappers. It allows us to do all these cool things. I mean, they hear two words like foreign and wrapper, which in this context don't necessarily sound that good, especially when you're talking about data locality and then you say foreign, they think, oh, you're obviously like pulling data over the network. And wrapper just sounds like some lightweight piece of cruft. Yes? SQL Med, yeah, would be a good option. But then the problem with SQL Med is you have to say like, oh yeah, but that's like a 10 or 15-year-old standard, and then that sounds boring, right? I mean, you want stuff to be new, and you want it to have this cool buzzword attached to it, and unfortunately, anyway, we should form a focus group, and we'll work on this. It's a good idea. So what I've started saying is that really foreign data wrappers are pluggable storage engines. It is an API for pluggable storage engines. And that's, to me, is what it looks a lot like, and it's what it allows you to do. And one of the ways, in fact, in which foreign data wrappers are more powerful than Hive SerDes is that they allow you to do filter pushdown. And once you have the ability to do filter pushdown, it becomes very practical to build a foreign data wrapper on top of a columnar format. So out of curiosity, by hands, how many people are familiar with like columnar data formats? Okay, cool. So some people, but not enough that I shouldn't explain what I'm talking about. So traditional databases, when they lay data out on disk, they use a row major format, which means that if you're doing a table scan, you basically read row 1, then row 2, then row 3, et cetera, et cetera. In a column major format, data is laid out like column 1, column 2, column 3, or perhaps a chunk of column 1, a chunk of column 2, et cetera, and then the next chunk of column 1, column 2. So there are these sort of like hybrid formats like RC file or PAX where things are chunked like that. The advantage of columnar formats, especially for OLAP databases where most queries are going to end up triggering full table scans, is that if you have a predicate well, let's be even more basic. Let's say that you're only looking at one of the columns in your query as opposed to doing a select star. You don't actually want to read those other columns off disk. I mean, we know that I/O is pretty much like the biggest bottleneck. So if you can do a seek over just a large expanse of data on disk instead of doing a read, as you would have to do with a column major format, that is like the single biggest performance benefit you can get right there. Another cool thing about columnar formats is the impact they have on compression. So people have known for a while now that if you have an I/O-bound task, one way of improving the performance is actually to compress your data. And this is sort of a little bit counterintuitive because you think, oh, well, if I'm using compressed data, I have to devote CPU resources to doing the compression and decompression. But it turns out that the amount of time it takes to do that is much less than the amount of time that you save in terms of doing the I/O to transfer the compressed data from disk into cache. And columnar formats make this even better because it turns out that most of the compression algorithms that people use will actually generate higher compression ratios if the stuff that you're trying to compress is like similar. So in other words, let's say that you have a string column, an int column, a string column, an int column. If you have to compress that data in a row major format, the compression ratio will not be as good as if you were, the other case, where you're using a columnar format where you can compress an entire int column followed by an entire string column. So this is like one of the reasons why we're really big on foreign data wrappers. For us, the ability to be able to like plug in multiple different columnar formats seems like a huge win, especially in the context of Hadoop, since right now there are several different competing columnar file format standards. And it's nice to actually have the option of supporting multiple formats as opposed to just one. And then this is my final thought about foreign data wrappers. So someone in the audience mentioned SQL MED earlier, which was the original like ANSI SQL standard that sort of outlined this idea of adding this sort of like standard for creating a level of indirection between the tables that you see in one database and actually having them redirect to data that's stored somewhere else. And the use case that people were thinking about 10 or 15 years ago or whenever it was when they came up with this standard was really database federation. And the problem that they were trying to solve was that enterprise organizations don't have one database, they probably have 10 or 100 databases. And that creates a big management problem, especially when you really want to be able to have sort of a unified view of all of your data. So if you're able to create tables that behind the scenes actually redirect to data that's managed by another table, that's a huge sort of management win. But what SQL MED, at the time I don't think anyone was really thinking about was what this would look like in more of a distributed systems context. And so let's think about it this way. Like, let's suppose that you have a single PostgreSQL instance and you have a MongoDB foreign data wrapper. You are able, from your single PostgreSQL instance, to push a filter down to MongoDB, but anything that results from that sort of like query then has to be pulled back across the network so that on your single node, let's say, you can do the rest of the aggregation that you wanted to do or something like that. Now, if you have a distributed version of PostgreSQL, you can actually co-locate the PostgreSQL worker processes on the nodes that are used by your distributed block store. Let's say MongoDB, HBase, or for example, HDFS. And then you can both push the filter down into, let's say, MongoDB, but once you pull the results back up, instead of sending them over the network, you can apply part of the aggregation in a data local fashion. So the amount of I/O that has to be done over the network is significantly reduced. So the point I'm trying to make, I guess, is that like there's federation and then there's distributed federation, and distributed federation is a pretty cool idea. Yes? So, okay, so we don't support inserts or updates in CitusDB, and that's part of being like an OLAP database. In terms of supporting transaction-oriented things in the underlying block stores, for example, MongoDB, I think, I don't know, what would you say? Actually, could we just save the questions for the end, just so I can get through the, I have like 2 more slides, and then we'll break for questions. Okay, one more point. So, one of the other reasons why we decided to build CitusDB on top of PostgreSQL, I mean, there are a couple of reasons, right? Like, why reinvent the wheel when you can build on top of something that's already great? Another reason being that, building a distributed database is more than just building a distributed query compiler and execution engine. It's also like all of these tools that sit around it. And I've definitely learned that the hard way from working on Hive, where you implement one thing and people are like, that's great, but what about these 10 other things that you haven't yet finished? But I think another thing that we've been really excited about is the fact that you have these 2 communities which are both very vibrant, which are doing great work, and we really see CitusDB as a way of sort of combining those 2 communities into one, or at least providing people on either side with access to the great tools that are produced by the other. So for people who are already part of the Hadoop community, here's a chance to use an enterprise class database and an enterprise class feature set on top of Hadoop while maintaining the sort of like characteristics of Hadoop in terms of scalability and cost effectiveness. And for PostgreSQL users, here's a chance to use the tools that you're already familiar with, but to use them on top of a platform that allows you to analyze petabytes of data. And also, in addition to that, we've sort of introduced this, I think, new level of flexibility with schema on read and features like that. So I just wanted to quickly sort of give some closing thoughts. So I think the first one is that it's a little bit unfortunate that we have this name Hadoop, which lumps together MapReduce and HDFS, because I think as a result people think that like these 2 components are inextricably linked together and that they're of equal value. And I mean, this is my opinion, but HDFS is much, much, much more valuable than MapReduce. MapReduce is not the only way to distribute computation across the data nodes in your cluster. I mean, CitusDB is one example of another way, right? Instead of using MapReduce, we have our own custom operator there, and we get a more efficient system, a more expressive system as a result. But I think the other thing is that HDFS is really what is sort of driving industry adoption of Hadoop. Because of the way that it commoditizes storage, it effectively sort of frees you from the clutches of the NAS and SAN mafia, and also, I mean, it's really changing the way that organizations manage data. I mean, the fact that it's so inexpensive compared to NAS and SAN technology means that this data that you were previously just writing to tape and effectively chucking, you're now keeping on site. And once you have it on site, of course, well, if we have it, why not query it? Why not try to extract some information from it? And that, in turn, is sort of driving this work to try to figure out how we can build, databases that look familiar, that provide this familiar feature set on top of this new storage layer. And this storage layer is significantly different from the storage layer that already exists in the enterprise. And it's these differences that sort of require us to devise this new architecture. So it may seem like a little strong to say that like this is a new generation of analytic databases, but I genuinely think that they are significantly different from the databases that evolved over the previous decade. And I think that description is warranted. So the other sort of closing thought just has to do with a summary of sort of the core benefits of SQL on Hadoop and more, more specifically PostgreSQL on Hadoop. So in terms of sort of new features, things that weren't possible before, we have this nice ability to sort of decouple the logical schema from the underlying physical data. So you don't have to do loads. So you don't have to wait for your DBA to model your data before you can analyze it. So it has both, I think, an impact on the way that you interact with your coworkers and your ability to like quickly run queries against things. It also has a very significant impact on the way that you utilize your underlying storage. If you have to load data into a database, you're not just transforming it, you're also copying it. So you end up with multiple copies of the same data in multiple different storage systems across your data center. Doing schema on read means that you have one copy, and you can even have the, you can even project multiple different logical views onto that data as sort of an additional level of flexibility. So another core benefit is that since we're building on top of a horizontally scalable file system and leveraging, the sort of key principle that makes it scalable, data locality, we're able to maintain those same characteristics. The same goes for fault tolerance. And then I think the key thing that sort of differentiates this new generation of distributed databases from Hive is that by replacing MapReduce, we're able to achieve low latency, which means that you are now able to do interactive queries against small slices of data, and that once again really changes the way that you can interact with your data. We're hiring. We really like PostgreSQL. We hack on PostgreSQL a lot. It seems like this is a pretty good audience, for doing recruiting. So if any of you folks are interested in perhaps getting a job or changing jobs, you should definitely talk to us. That's a link for our website. We also have a bunch of interesting blog posts, and also another cool thing is you can actually download a copy of CitusDB, install it on your machine, and take it out for a test drive. We have EC2 images available, as well as I think CentOS and RHEL RPMs. Okay, questions? Yes. The license. Samid, actually, I'm going to. So parts of it are open source and parts of it are not open source. So all of the foreign data wrappers that we've written are open source. The code that we use for syncing metadata off of the Hadoop name node is open source. The parts that are closed source right now are basically the distributed query planner that we wrote. I don't think that we, speaking for my coworkers, I don't think we have any sort of like inherent objection to at some point in the future possibly open sourcing this. It's more of just a like, we can't do that right now, right? That's how I'd explain that. Yes?
Is there a certain threshold of data amounts and stuff where kind of moving away from just doing a Postgres querying versus going against this kind of additional legwork of at least the architecture and hosting all these various servers and whatnot? Is there certain, I mean, you kept talking about petabytes and
right.
upper terabytes, but
so I would say like if you're getting close to like let's say 10 terabytes of data, that's probably where this becomes a practical solution. Most cases, like I think we have two different types of customers. So one customer sort of like archetype are people who already have a Hadoop cluster set up. And they're using Hive, but they're like, man, I can't stand the latency, or I really wish it provided better support for SQL, or I already use PostgreSQL and now I'm using Hadoop and I really wish I could run one on top of the other. Then we have other customers who are doing things at, let's say, like terabyte scale, right? So they're running PostgreSQL, but it's starting to sort of slow down a little bit and hiccup, and they know that they need to go for a distributed solution, but they're not necessarily interested in setting up their own Hadoop cluster because that adds this additional management layer. I didn't mention it in the presentation, but CitusDB actually has two different deployment modes. So in one mode, you deploy it on top of Hadoop, and HDFS basically manages the storage. In the other deployment model, every worker node basically runs PostgreSQL, but it runs on top of the native file system, like ext3 or ext2, in which case it just uses PostgreSQL's storage engine for managing the table shards, basically.
And then you'll be using Postgres foreign data wrappers too?
We would not actually use Postgres foreign data wrappers. We would actually create basically like fragment tables on each one of the workers, using basically like the size of these fragment tables is configured, and then when the user loads data into this sort of like distributed Postgres database, we sort of in parallel then stream data into these different fragment tables on the worker nodes. Yes.
I have a basic question about EW. As far as I know, here only allows only predefined queries.
No, it allows. So
How can we push down the output query to other databases?
push queries.
Push queries down to different database or
Right. So it's basically up to the implementer of the foreign data wrapper to support things like that. So you have the ability right now to let's say extract filter conditions, which are something that are easy to push down, but you have to re-express that in terms of the API of the thing that you're talking to, in terms of the thing that you're building the wrapper on top of.
So function could be defined could be a change.
Change
At the runtime.
change the runtime.
I tried to create a DW
Mhm.
before. I starting with run output query to different database.
Mhm.
So I didn't know DW can have different conditions.
Okay. Let's take this question offline. I'm not sure how to answer it right now. Question? Mm-hmm. So the question is, if you have a complex query, can you gather all of the data to one local site? I'm not sure I understand why. What problem are you trying to solve by doing that? Or okay, sure. So for example, the join, right? A join that references multiple tables. So there are different strategies in distributed databases for doing joins. So one strategy that we support right now is a broadcast join, where if you're joining a small table with a large table, you can broadcast basically or copy the small table to each one of the worker nodes so that it has sort of a local copy. There are other strategies for doing big table joins in a distributed fashion that we're working on implementing right now. But the basic thing, the basic issue, right, when doing a big table join is that you do have to transfer data between the different worker nodes, because you can't expect that any given worker node will have all of the data locally stored that it needs in order to process like its fragment of the join. And the algorithms that have evolved for handling this distributed join case basically try to minimize the amount of data that you need to transfer. So there are different strategies. In our case, it's a little bit more complicated since we're not able to basically assume anything about the underlying data in each block. Since storage is completely delegated to HDFS, we can't do some of the optimizations that you see in other sort of more traditional MPP databases where they pre-sort or they hash partition the data across the nodes using a strategy like that. Make sense? Okay. Question? Yeah, so you basically use our version of the copy command. So like I mentioned earlier, there are two different modes for operating Citus DBN. So if you're in mode 1, where you're actually using PostgreSQL's storage layer instead of using Hadoop, then you would use our distributed copy command, and you would basically say, here's the file, and I want you to copy it into the following table. And it would then, in a distributed fashion, basically stream that data into each one of the worker nodes. But in the typical sort of like OLAP use case scenario, the data that you want to process is like fact data, or it is log data. So it's not stuff that you're actually going to manipulate. You basically want to do joins or aggregations or analytic SQL queries on that information. And then in the case of deployment mode 2, where it's running on top of HDFS, you would use the Hadoop tools for basically loading data in. So Hadoop has something called distcp, which is a distributed copy program, which is typically used there. Any other questions? Yes.
I was just thinking about this, and one of the things that we do a lot is casting users across our, because we have a cluster we build out native Postgres, and we have locality that we can pass partitions, so we can kind of use per node and then push that data out and sum up the results of those counts and then send that off. And that's a lot of what we do actually. I'm trying to figure out how you would do that on this system. It seems almost impossible.
Right. I'm going to actually let Samid answer that because he's been working on this recently. For the Postgres version, we can. For the Hadoop version, we can't. Yeah. Any other questions in the back?
So back to the consistency isolation question I asked earlier, does the deployment node 1 where it goes into Postgres, does that offer those capabilities or those guarantees?
Samid? Yes, question.
I missed the part where you say where you're using the streaming replication from Postgres.
So we're using that at the master node level in order to replicate the table metadata that the master node maintains. So this is basically information that maps a global table name to all of the foreign tables that exist on each one of the worker nodes. So it's basically the table metadata, both at sort of the global master level as well as the mappings from the global level to the worker level.
Because your streaming replication is cluster-based, right? So you have to replicate the entire database, the entire cluster to all slaves, right?
Mm-hmm. Which is what we want to do, because there's a single master or a single active master, but you could have, with streaming replication, multiple hot standbys, okay? And we're not interested in replicating, in a sense, real data because no real data exists on the master. It's all metadata about basically where the shard records are stored on each one of the worker nodes. Any other questions? Okay, thank you.